Okay, so now we are going to discuss the performance and security measures of S25. So before we go into this, I want to apply MMI minus 1 condition on, let's say I want to apply it on BB84. Of course, this performance is going to be looking at number of extra calculations that need to be done. So this is going to be the first calculation that we have to do. For BB84, let's say I have n number of messages. So I have n number of messages, uh, uh, sorry, n number of kind of keys that we are talking about. So out of all of these n number of keys, there is going to be one bit of ambiguity, and then what actually happens is we are going to look at the number of keys that it can possibly generate. I know that this kind of skews the favor of performance towards BB84 because we usually use one message to actually get the key across. And of course, in that, if the error happens on the bit we reject, then it's not going to be looking good for BB84. So let's assume that there are n number of keys, and then we apply the correction bias and everything. So MMI minus 1 on n. So on first message, so first key which is going to be sent, there are n minus 1, sorry, uh, yeah, so there is one bit of ambiguity, which means there are two possible cases. So firstly, there are two possible cases. On second key, again two possible cases, and so on. So essentially, the number of keys that I'm going to be looking at is going to be 2n. And of course, when we talk about these kinds of things, I have to also include the original message. So it will be 2n plus 1. Okay, so since we have all of these, and then every one of them is equally likely to be the actual key, I don't think original is required. No, I don't think original is required. So it's just going to be 2n. Okay, so if we were to combine all of those keys, then I'm going to have 2n bits of ambiguity. And then of course I can include the statement saying that maybe we don't know where the exact bit is going to be there. So this is the scaling of MMI minus 1 on BB84. Of course, it is not great, but it is expected of BB84 because it does not amplify anything here. So it is just the quantum protocol. So this is the case, and then let's say if I don't know where the bit is actually present, then it's going to be another factor added into it. Yeah, so it's going to be somewhat, it's going to be quadratic or polynomial in nature. So now let's apply the same thing for S25. And again, we are talking only about the number of extra operations that the receiver has to do. So uh, again, to calculate this without any assumptions is going to be very hard. So what I did is, since I cannot calculate every single possibility on every single bit, what I'm going to do is, I'm going to make this assumption. I'm going to be making the assumption that there is either 1 or 0 bit lost, 1 comma 0. So in any possible key, there's either 1 bit which is missing or there are 0 bits which are missing. And then the person doesn't know exactly where the missing bit is. So again, if we do that for the BB84, we get 2n times k. where k is the number of messages. Um, or we can even write summation of k. So again, this is not too bad. This is quite good. But let's see what happens in S25. So uh, I cannot prove it for every single case of mistakes that are going to happen, because if I start to do that, then I might not even come to an answer. So I'm going to take a subset of this particular condition. So of course, the idea is the one bit can be missing in either. So let's say I have k1 to kn. This one bit can be missing either in k1 only, or k1 k2, or all of these kind of things, and also k1 k3. There is no k1 k3 here, it's just k1 k2 k3, but there is possibility of k1 k3 and also possibility of k1 k4 and so many more combinations. But what I'm going to stick to is going to be this sort of thing. So I'm going to start with 0 0. So I'm going to build a matrix system 0 0. So what this 0 0 tells me is that there are absolutely no mistakes, which means there is one possible state here. So the next one is going to be 0 1. So this 0 actually represents n, or on the nth message. So this 1 represents just one before that. Uh, so to clarify what these numbers mean, this number is the starting of error. So whatever number there is here, that -1 is going to give me the instance of the message where the error has started, and this is going to be the end. So of course, now we have some instances. Now we can kind of take care about it. Okay. So we need to calculate all of these values. Um, if it occurs on just the step before, then I'm going to be having a quite bit more. I'm going to be having specifically 2 times uh, k. So k, I mean, like, if this is 1, then this is exactly 1. Sorry, k n minus 1 times 2 to the power k n minus 1. Okay, so where does this number come from? So where does this number come from? So when we look at the reduction of states, 2 times k to the power n minus 1, this comes from the BP84 single message thing. So this additional factor is going to be the extra number of states that he has to look at, because if these many messages are there, the receiver also looks at 2 to the power kn minus 1. So, but for each of these messages, he has to look at 2 to the power kn minus 1. So that is the number of states that he has to actually look at. Of course, it's linear in k n minus 1, and of course, it just kind of keeps growing. So this is going to be 2 times k n minus 1, k n minus 1, 2 to the power k n minus 1. So now let us look at what happens on 0 2. So what exactly happens on 0 2 is, I have there is going to be the mistake started on that particular uh, bit, and then what I'm going to be getting is 4, because there are 2 mistakes here and it ends at 0. So I have 4 times k n minus 1 times k n minus 2 times 2 to the power k n minus 1 plus k n minus 2. So if I keep writing everything down, the entire board is going to get extremely messy. Um, so yeah, whatever it is, I'm just going to write it down. 4 times pi of, I mean, like, yeah, I mean, in the actual thing, you can just write pi of, you get 2 to the power some I times pi of kn. But here I'm going to write 4 times kn minus 1, kn minus 2 times 2 to the power kn minus 1 plus kn minus 2. Okay, so now again there is going to be 2 to the power here. So this is 2 to the power 0, 2 to the power 1, and then 2 to the power 2. So what I can do is I can write the series as so. So R of AB is going to be number of states where the start is A and the end is B. What I'm going to get when I do all of the things is 2 to the power. If we look at these values, they are going to be shifted. So this value would come here, this value would come here, and so on and so forth. So I'm going to be getting 2 to the power A plus B. And then I'm going to be having this sort of this exponential factor. So again, I'm going to drop this kn factor because of course it is just multiplication of the numbers. So that's a linear factor for each key. So I'm going to ignore that, and then I'm going to say, okay, so 2 to the power a plus b plus I have this summation j equal to 0 to b kn minus j. So this is going to be my RAB. So now what we see is, because everything is shifted, I can, so let me write it down how it looks. So for 1, it is going to be 2 times kn minus 1, 2 to the power kn minus 1. And then for 1, 2, this is going to be 4 times kn minus 1, kn minus 2, 2 to the power kn minus 1 plus kn minus 2. So again, everything is just shifted diagonally. So I can just take the diagonal elements and so on. So the total number of states, which is going to be summation of A and B of RAB, is going to be okay. So let me just. So this is the method which I used. Of course, there are multiple such errors which I'm seeing. So errors which begin and end more than once. So I'm ignoring that. So summation RAB is going to be summation of, let's say, I equal to 0 to n, I plus j plus 1 2 to the power I plus j plus summation of j equal to 0 till I kn minus j. I and j are the kind of start and end positions. Okay, so what we have done is we have taken, so if this is the set of errors, I've taken a small subset and then I'm dropping off some of the elements. So I'm taking even smaller subset. And when we look at the final answer, we get a summation from I is equal to 0 to n, and similarly j and I go from 0 to n. And then we have an exponential term. And of course, it is an exponential in both I and j. and this exponential is going to be repeated until n. When compared to BB84, this is much larger, just because it amplifies it much better. Yeah, of course, I'm missing another factor here, which is going to be a pi. I mean, like the multiplication of kns, but it's still okay. And this is going to be the number of states that the attacker has to look at. So if all of these states are equally probable, like we talked about in MMI minus 1 0, so um, what I'll be getting is, of course, like if I want to ignore the original state, I can just remove this. And now we can be clear, but we can add this to make it a little bit nicer. Um, so we have the probability of choosing the correct state. It's going to be 1 over summation of RAB. So when we do sum over RAB, we are going to get this massive sum, and of course the number of operations that needed to be done is going to be much larger. So this is just for an arbitrary system without any LRM, without any of the other stuff. But it does, what this proof assumes is, attacker has capital K superscript n. So this is the original file. He has access to the ECCs. He has access to the entire quantum channel except for the whatever MMI. And then he knows the final decode algorithm. This is without LRM, and even though he knows he knows exactly how the protocol works and he knows exactly what is going on, he has the exact file along with the exact error correction codes, along with the exact basis. He still has to choose one particular state from this whole thing. Okay. So that is for an arbitrary case. Now let us take the step further, and while I am doing LRM, so I'm going to take the least scalable part of the smallest LRM, which is going to be 0, 1, 2 and 3. So the reason I cannot take 0 and 1 is because when I try to apply some sort of encryption, then the algorithm actually becomes deterministic and not the exact value here. And let's say I apply the same for BP84 and I'm going to do it for 3 messages. So using BP84 I have sent 3 messages, so I'm going to get something around like 1 over 8. If he knows exactly where the bit is located now. Okay, so let us look at for, of course if I look at the implementation of LRM and everything, I am still going to get 1 over 8, but there is no partial key access, which is another layer of security that S25 offers. So again, we have this kind of a situation. Sorry, let me just by 8 get key. So, but using MMI, there's already a partial access. So for S25, yes, the after everything, the thing is going to remain the same, the probability, because in this case, what I've done is I'm assuming the attacker has K superscript n, LRM module, encryption scheme, decryption scheme, and then final key selection scheme. So if the attacker has all of these things, he still has 1 over 8 chance of getting the key. Whereas for BB84, all he needs to do is just take off the qubits and apply an X or a Z gate and then finally perform the operations. But again, even with all of these things, S25 has 1 over 8 probability without redundancies. So it's 1 over 8 probability to get the final state. So when we look at this, you might think that both of them are the same, but the partial key access is not present for attacker in S25, and all of this information might not be that easily available. So let's say I take k of n to be completely arbitrary, and I'm going to set it in packets. So what the attacker ends up is around 85% of k superscript n, and if any of these are not with the attacker, then it becomes almost impossible to decode the final state itself. So till here, if he doesn't have any of these things, or if there is some ambiguity, it just scales up extremely quickly, and then he's not able to access the final state. So if he doesn't access the final state, he cannot access the final key. So even if he knows the final key scheme, he's not able to get access to it very easily. And then there is a huge thing with this partial access as well. So maybe if uh, those messages are extremely dissimilar, then there's going to be a huge issue. So out of these 8, there can be so many other uh, kind of collisions that are happening. Again, this assumes that the attacker has a much better quantum computer with access to everything. So now let us just take out the alarm. So he doesn't have access to the alarm. So let's see what he has to actually get. So of course this is with access to alarm, and of course he knows this set, and then he knows everything else. So what he's going to see after the final thing, he has to um, first of all he has to kind of guess what the actual um, language code is. So this is going to be 1 and 2. Then he has to figure out what exactly I am trying to send, and then if there's a bit missing, then if there are 2 bits missing, then it becomes even more kind of messier. And of course, if he keeps on, if the number of messages are very large, you can somehow reduce alarm. So let us now eliminate kn. So once I eliminate kn, it becomes almost impossible because so again, if this is not there, it becomes completely impossible for him to do anything with the messages which are being sent, because the attacker space is going to be the entire k of n, and the problem is not the you know uh, not having the partial access. The problem is when he looks at something like this with a quantum computer, what he is going to see is he's going to see every single possible combination of sentences, which of course we cannot solve. So that is where the collision comes to the rescue. If he doesn't have access to the encryption scheme, then he cannot look at any encryption, he cannot look at any decryption. And of course, if he doesn't have the final key, he can get the final state, but there's always an ambiguity of where the actual final message starts or how the final message looks. So if he doesn't have access to any of these things, I mean, like it becomes almost impossible. So yeah, under the lowest scaling and under S25 being at a very huge disadvantage, S25 equalizes with BB84 with the same probability. And of course, if I start to add redundancies, the redundant bits can also be the redundant bits will also offer another layer of encryption, because even though he'll get the sentence, he might not get the actual redundant bits, and then he cannot find the state in which I'm actually talking about. Um, in the case that he does not get, uh, again, if I include distance bit for, let's say this is the final distance between uh, the message and the alarm, his space is not going to decrease by that much because he actually doesn't know what the distance is, and then he has to consider every single possible combination. And even though it is somewhat possible, it is very unlikely that he is going to find his space is going to reduce in such a way that it is going to be somewhat meaningful to get the correct answer. So let us just write everything down. So I'm assuming that the attacker has everything except this particular thing. So if he doesn't have access to this, it is impossible. So even if he sits inside the quantum channel and gets every single bit without actually getting anything under MMI conditions, without Kn or even let's say partial access to Kn, it is almost impossible to get the final key. So if he doesn't have access to the LRM, then it is somewhat possible. So it is somewhat possible, but again very unlikely. So this is because how the LRM is going to be structured, and if it has much more complicated rules. So right now we have discussed only odd, even odd, and so on. But of course I can build a much more elaborate LRM. Again, if I were to include it in AI, then I can filter out some other edge case sentences and everything else. So without access to LRM, it is somewhat possible if n is high enough. So what actually tells what actually the problem here is going to be the fundamental problem faced by all when we are looking at any sort of sequences. So if I were to give the sequence 2, 4, 8, 16, the next answer can either be 31 or 32 depending on what exactly my sequence says. So most of us would assume 32 because of the sequence, but there is a possibility of 31 with some clever geometric constructions. Uh, and without LRM, this kind of problem emerges. So without encryption or decryption scheme, without encryption decryption scheme, one thing is for sure. And again, for LRM, it might be so that the distance bit is somewhere in between. So again, if n is very high, then we can have some kind of information on the alarm if he doesn't know the alarm. So without the encryption decryption scheme, uh, it is again almost impossible because we don't know exactly what is going on or how the encryption process is happening. So I would say impossible. Though if k of n is somewhat, how would I say, if it's somewhat small enough, the set of words are small enough, it might be possible somehow, but I would highly say it is not possible at all. So with our final key, we have excess collision. So with this excess collision, again, there is no telling what exactly happens, and it is almost impossible to kind of eliminate all of these collisions. So again, so when we look at the final form of S25, it resembles the first module where I introduced S25 by saying some random sentences lead to a particular code. With all of these things, it looks like it is somewhat similar. Uh, is there anything I missed? Of course, error correction codes. Without ECC, the bits in themselves don't mean anything. Of course, that happens even with BB84. Okay, so that is the performance and security of S25. Um, yeah, without KN is impossible, without LRM it is possible. Okay, so now what happens if one of the messages is missing? So if a full message is missing, then we don't really know how many messages can. I mean, like if we know that one full message is missing, then we would have to try out all of the LRM cases that we know. And if by some miracle it still works out, again the chances are very very little when you consider some complex LRMs. But with the lowest scaling, it is still equal to BB84 and provides a partial key kind of block. So the question is, what actually do we require to crack open? Of course, we require all of these things, and we do require a little bit of luck over all of these things. Uh, and that is the only way that S25 can be broken, especially with MMI-1 being enforced by physical constraints. So that is all for S25 performance and security. What I've shown might look a little complicated, but I'm pretty sure it's manageable. And I'm hoping I've covered everything. Yeah, I've covered everything. Thank you.